Hey guys, this is the second video in our series about chemical equilibrium, and this one focuses on K, the equilibrium constant. As we said in the previous video, K can tell you quite a bit about whether you have a lot of product or reactant or relatively equal amounts of product and reactant. For example, an example of a reaction with a small K would be nitrogen gas reacting with oxygen gas to produce the highly deadly nitric oxide, which is also a gas. Luckily, these two gases prevalent in our atmosphere only do this to a very small degree. K for this reaction is 1 times 10 to the negative 30. 1 times 10 to the negative 30, oh, that's a really bad 10 to the negative 30. Let's see. 1 times 10 to the negative 30 tells us that this reaction is almost exclusively lies to the left. That there is basically almost no product at all formed. So basically, when something is as small as 10 to the negative 30, you can pretty much assume that there is none of this. That if we were to draw this with arrows representative of which direction the reaction lies in, whoops, wrong way, we would have arrows that look actually like this. Very much so to the left and almost nothing to the right. But we don't really do that very often. We normally draw them in both directions the same length and then express it with the KEQ. So with a KEQ of 10 to the negative 30, basically there is almost no nitric oxide produced. A second reaction that does happen quite easily is the combination of CO, carbon monoxide gas, with oxygen to give us carbon dioxide gas. This K is 2.2, or about 2 times 10 to the 22nd. If it's 2 times 10 to the 22nd, that tells us there is lots and lots of CO2 in this equilibrium and almost none of these reactants left over. And a third reaction with a much more intermediate level of K would be, let's say, the reaction of BrCl, a gas, with, let's see, to produce bromine and chlorine gas. In this reaction, K is a value of 5. And what that tells us is that we have relatively similar amounts of both products and reactants. Let's take a numerical example of where K might come from. Let's look at the production of ammonia gas from hydrogen gas and nitrogen gas. Let's see if we can calculate K. If you were told at equilibrium the concentration of this gas were 3 molar, the concentration of the hydrogen gas at equilibrium was 2 molar, and the concentration of the ammonia gas at equilibrium was 1 molar. How do you figure out what the equilibrium constant is? Well, the equilibrium expression can be written directly by looking at the balanced chemical equation. We take the products, in this case NH3, and we raise them to their coefficient's power. you divide the products by the reactants multiplied by one another. In this case, N2 multiplied by H2 raised to the third power. Because the nitrogen has a coefficient of 1, it's only raised to the first power, so we're just going to ignore it. So if given the equilibrium concentrations and the balanced chemical equation, you can determine the equilibrium constant for a reaction by simply plugging in this manner. The ammonia's concentration is 1 molar, so 1.0 squared, divided by 3.0 times 2.0 raised to the third power. Plugging into our calculator, we get 0.042. And what this would tell us is if these concentrations were our equilibrium concentrations, once the reaction were allowed to reach equilibrium, we could calculate our equilibrium concentration to be 0.042. 0.042 is neither very large nor very small, indicative of the fact that you'd have, similar concentrations of reactions and products at the time of equilibrium is reached. Another thing to note is that the equilibrium constant has no units. The general term, or the general way we calculate equilibrium constants for any generic reaction where the products are C and D and the reactants are A and B, and the lowercase letters are the coefficients in the balanced chemical reaction. We can look at the balanced chemical reaction, and we put products over reactants, and the products are raised to the coefficients in their balanced chemical reaction, and they're divided by the reactants raised to their coefficient powers. Now K represents once a reaction has reached equilibrium. There's another concept, or another number we can look at called Q, called the reaction quotient. It's calculated the same way as K, but Q is a snapshot of the reaction at any given time. Q may be before, this snapshot may be taken before chemical equilibrium has been reached. It's possible that Q represents a snapshot taken at chemical equilibrium, and it can tell us which way the reaction needs to shift in order to achieve chemical equilibrium. So Q is calculated the same way K is calculated. However, if we take our reaction above, let's say for the production of ammonia, if K is 0.042 in this case, if we plug in values at any given time, if we know that the concentration of species of the nitrogen, the hydrogen, and the ammonia at any given time, and we plug them into this paradigm, and we get a value that is lower than 0.042. So if Q, the reaction quotient, is less than K, what that means is the reaction needs to shift to the right to produce more products. If, however, Q is calculated and Q is greater than K, what that means is in the particular state the reaction is in, there are more products than there should be or there will be at equilibrium. And so if this is the case, the reaction shifts to the left to consume the products and to produce reactants. And if Q, the snapshot, is equal to K, that means that we are at equilibrium. An example of this, an application of this would be, let's see, in the above reaction I'm going to go up, but let's just say at a particular time I'm going to erase the values of 1, 3, and 2. And let's just say that our equilibrium constant at this temperature is, we've determined, or we know that it's 0.042. If instead we have 3.0 moles of this, 6.0 moles of this, and 0.5 molar of this, and we plug these values into our equilibrium expression, but instead of calculating K, we are calculating Q, the snapshot at any one time, and so I'm going to call it Q, and we plug these values in. 0.5 squared divided by 3 times 6.0 raised to the third power. We get a value for this, Q, equal to 3.9 times 10 to the negative 4. And because Q, the snapshot concentrations, equilibrium at this time, is smaller than K, what this means is that the equilibrium needs to shift to the right to reestablish this value. So the reaction will produce more product such that this number here will go up and these numbers go down. These concentrations go down. And that happens until this ratio is achieved. And if Q is less than K, what that means is these values have to go up and the reactant concentrations have to go down in order to achieve this ratio. So more of the reactants will get consumed to make a little bit more product to get that ratio in order to make K. If, on the other hand, we have a situation where when we plug these numbers in, the ratio is greater than 0.042, what that means is in order to achieve equilibrium, this reaction would have to consume the product, NH3, and produce more N2 and H2 to achieve that ratio. So let's summarize what we talked about. The size of K can tell you whether or not you have lots of products or lots of reactants or relatively equal amounts. A very small K tells us that we have almost no product. A very large K tells us that we have almost exclusively product. And a moderate level of K tells us that we have relatively equal amounts of product and reactant. If one has the actual equilibrium concentrations of a reaction, you can determine K by plugging it into this equilibrium expression, where we take the products raised to the coefficient in the balanced chemical equation divided by the reactants multiplied by each other, raised to their coefficients. And if we have not the actual reaction equilibrium per se, but just simply a snapshot of a reaction at any one time, we can plug, and we know those concentrations, we can plug them into our equilibrium expression and compare them to K. If Q is much smaller than K, the reaction has to shift to the right to produce more products to achieve equilibrium. If Q is greater than K, the reaction has to shift to the left to consume products to achieve equilibrium. And if Q is equal to K, then we have in fact achieved equilibrium. The next video is going to focus a little bit more on the difference between gaseous equilibrium and reactions that take place in aqueous solution.